it might take, years or decades to become, an expert, like in a whole field, and you might be very far from that, but it really doesn't take that long to become the world expert on one particular tiny little problem, right? And so try to become the world expert on something, even something very, very narrow.
So Professor Aaronson, can you tell us a bit about your early journey? You were a young prodigy. You graduated high school at the age of 15, got your PhD at 22. Can you tell us about that?
Yeah, well, I didn't really graduate high school when I was 15. I got a GED from New York State, but I was not happy in high school for several reasons. I mean, just socially, academically, and I wanted to get out. And I mean, I was in a weird situation because um, I went to public school in the U.S. for junior high, and then in Pennsylvania actually, and then my parents moved to I lived in Hong Kong for 1 year because my dad was working there, and because of the I went to an American international school there, but because of a mismatch between the way they did things in the U.S. and in Hong Kong, I was not able to do math that was appropriate. I guess I had always been sort of ahead in math, and so the only way to deal with that was for me to skip a grade and skip and go to the high school. And once I had done that, that was sort of a something flipped for me, right? That I could actually do this. I could get out of this environment. Where I really wanted to be was college, right? I wanted to be in a place where and of course I somewhat had an idealistic view of what college was, but a place where ideas would matter more than popularity, and where you would be able to choose what to study and advance at your own pace, and all of these wonderful things. And so then I returned from Hong Kong to the U.S. and was in a public high school for a year, and as I said, I didn't like it, and and then I ran out of math to take. Right, I took the AP calculus, and then my parents basically suggested to the school, well, why doesn't he just do online learning, right, and do like differential equations or whatever with the Stanford has this EPGY program, right, where you can do these things, and my parents said they would pay for it. The school said no, that's so I sort of seized on that as my excuse. I think I had just seen a brochure for a place called the Clarkson School in upstate New York, which is a part of Clarkson University, but you can live there for a year and take college courses, but it's for high school students, right? I said, even knowing very little about this, I think, I want to give this a try. And my parents, allowed me to do that. We had the car all, packed up to drive there. And while, when we were about to leave, then finally, there was one, actually math teacher at my old high school who was very, very good and who was, trying to advocate for me. And he was like, okay, guess what? I just got it so that Scott can take the EPGY program. And we said, too late, sorry. And so I went to Clarkson, and I generally had a very good experience there. I mean, socially, there were a lot of the same problems as at high school, but at least I was I was able to take courses that were a lot more interesting. I was able to sort of meet professors, get started doing research, and you apply from the idea is that after a year at this Clarkson program, then you apply to colleges as a freshman, but with a year of college credit. So I did that. Just very disappointed at the time at how things turned out, because I got rejected from almost every college that I applied to. I had a very weird background, but I was lucky that Cornell and Carnegie Mellon were kind enough to accept me, and so I decided to go to Cornell. But then there was one problem, that they required a high school diploma before you could enroll there, which I didn't have. And so we realized that I needed a GED from, okay, my old high school, oftentimes one's old high school will just give you a diploma after you've gone to Clarkson. My high school would not do that, because they said I was missing phys ed. I would have to spend the summer doing phys ed. But and then New York State said, well, we can't give him a GED because you have to be 17 to have a GED, and he's 15. My mom eventually convinced them to make an exception and give me a GED. So then I went to Cornell. I mean, I've met other people who were homeschooled, who actually did things that were more radical than what I did. I mean, I was accelerated by 3 years. That was all. And then after I was in college, I didn't really accelerate anymore, because I felt like I was in an environment where I wanted to be. And from now on, the main limitations were internal. They were no longer external.
Was it intimidating being in classes with people 3 or 4 years older than you?
The truth is, I would say the majority of them didn't even know that I was younger. If they knew, it was like maybe an oddity a little bit, but then they didn't care that much, right? I mean, because it's not like I was a 10-year-old, right? I was by the time I started at Cornell, I was 16 by then, and so I feel like academically it was fine. I mean, the main issue was social, right? I mean, and my parents had warned me that, okay, if to skip grades is going to completely screw up my social life, and it's going to make dating incredibly difficult, and so on and so on. And I sort of brushed all of that aside, and of course that all turned out to be true. I got my PhD before I learned how to drive, really, or learned how to have any kind of a social life, to speak of. I mean, or any kind of a dating life, really. But so I did things in a weird order, you could say, and that did cause an enormous amount of stress for me. But my main argument was that I was already socially unhappy in high school, right? I was already miserable, without having skipped grades, and so I felt like as long as I'm going to be miserable socially anyway, as it seemed at the time, I would be, at least I could be learning stuff. At least the academics could be better.
Yeah. And as far as the academics go, what were the advantages and disadvantages of specializing so early?
Well, I mean, I don't get to rerun my life multiple times and compare. But I think that mainly I'm grateful that I had the opportunity to to sort of learn about stuff that interested me, right? And it it was not just, that, I wanted to take only math and CS and nothing else, right? It was not like that. I mean, I took, plenty of humanities in college, right? And, but, I wanted to sort of have some freedom to, I pick what to learn about, right? I mean, like in high school, humanities means, the 5-paragraph essay, right? It means, you basically have to regurgitate what the teacher wants from you, right? And, if you try to, do your own thing, write things in your own way, then you will actually fail, right? And, this is, I learned this from experience, this is not theoretical, right? And, so even the humanities, right? I was a lot happier with in college than I was in high school. So it wasn't just a matter of specialization, but partly it was. I mean, I think that by the age of 16 or so, I knew what I was passionate about. It was the fundamentals of computing, right, and understanding what computers could or couldn't do, and I was ready to be learning about that and working on it. And I think that there is, the entire concept of, of sort of teenagerhood, right? That like people are from the age of 12 to 18, or now maybe even 20 or so, are still basically children, right? I think that that's largely a modern construction, right?
Huh.
If you go back even a few hundred years, by the time someone is a teenager, they're an apprentice, right? They can work, they can be learning while they're also, working, and they can be learning, the trade that they choose. And so I think that's actually natural, right? I don't feel like I'm that unusual in that respect. I think, I mean, maybe, unusual in some respects, but not in wanting to sort of get started with life when, I was 15 or 16.
Yeah, I had Tyler Cowan on the podcast, and he started. He knew he wanted to be an economics professor basically in his early teens, and he was reading and preparing for that from that time on.
Economics professor is not what one often thinks of as like a child, or an adolescent realizing that they want. But that is in the case of Tyler Cowan, I could easily believe that.
Is there some special advantage of learning the fundamentals of the field you're going to go into early on? So except for the fact that you just get more years to accumulate knowledge, is there the special advantage of learning it in your early years?
I'm not sure. It's a very interesting question. I mean, one could imagine that, while someone's brain is still developing, right, that it's good to be exposed to certain things at that age. And, I mean, like we know examples that are like this, right? Like, an obvious one would be learning languages, right? Where, there's a window where, children can just soak up languages, like a sponge. And, after that window, you can learn a language, but it will be a difficult, intellectual puzzle, and you'll never speak it as well as a native 5-year-old will speak it, right?
Yeah.
So it could be like that, but it could also be that like our brains are not really adapted for learning any of this stuff, right? I mean, like when we get to theoretical physics, theoretical computer science, and so on, right? All of it is like learning a language that we don't natively speak. Right, and on that model, it would just be a question of getting a head start of how much time you have to spend on it. I would love for someone to research that question, because I don't know the answer.
I have heard, as you know, like many of the important discoveries in quantum mechanics were made by people who at the time were very young, right? And that's an interesting fact. Not only did they learn that stuff early on, but like they made those contributions early on.
Yeah, but that's not just quantum mechanics. I mean, that's all over, math and physics, right? I mean, Newton was, about 22, right, when he, had his miracle year, of inventing calculus, discovering the laws of mechanics. Yeah, I mean, no, by I'm already old by the standards of math and physics, right? Which is weird to think about. Uh, there are also many examples of great contributions that were made by people in their 40s, their 50s, their 60s, right?
Hmm.
That's another empirical question that I wonder about, right? Is it that people's brains actually slow down as they get older, or is it simply that they have less motivation or less free time? Right. I mean, in my case, having two kids, has clearly given me enormously less time for research. Right. And, like in those cases where I'm, traveling, where I'm, away from the kids for a week, maybe like I can work again, and it feels a lot like it did when I was in my 20s. Right. And so, and then there's also the issue of motivation, right? That like when I was before I was established, like my entire conception of myself, my entire uh, goals for my life were wrapped up in succeeding in research, doing whatever it took. And now it's more like I have all kinds of other concerns. I have my own students to worry about, my postdocs, my kids, of course, my blog, the popular things I write. And research just feels like one more thing that I do, right? That my identity is not as much wrapped up in. So I may have also gotten dumber, right? That's certainly possible, right? But it's hard to disentangle from those other factors.
Yeah, you're the third person, and I promise we'll get to the technical questions eventually. But you're the third person on the podcast I'm about to ask this question because it fascinates me. Miracle years, as you mentioned, it's not just that people make like very important discoveries at young ages, but they make lots of seemingly uncorrelated important discoveries at young ages. So as you know, like Einstein did Brownian motion, special relativity. What was
Yeah.
the third one? There were two or three more.
There was the photoelectric effect.
Yeah, that's right. And these don't seem, superficially at least, to be related, and yet it's interesting to happen in the same year. What do you think explains that phenomenon?
In the case of Einstein, I mean, you're asking me to explain Einstein's miracle year. I mean, that's a tall order. I mean, one can say certain things, like one can say that physics in the early 20th century was ripe for these for these interrelated revolutions, right, of relativity and quantum mechanics, right? I mean, if it wasn't Einstein, it would have been someone else, not long after, with all of those things. General relativity, which took Einstein a decade longer, that was the one thing where if it hadn't been for Einstein, then for all we know, it might have been decades before anyone else did that. But the stuff that he did in 1905, I mean, they were all things that physics was kind of ripe for. Maybe it took, one person just looking at things in a sufficiently different way. I'm not sure really, but also it might be, the confluence of all of those things is part of why, we think of Einstein as Einstein, right? There were many other great physicists, around the same time, who may have done, one or two things of that caliber, right? But only Einstein does
Right.
does three or four of them.
I'm glad you brought up the topic of like ideas being in the air and ready to plug, because this leads me directly to the next question. I was rereading the lecture notes from your quantum information science class, and there's the lecture on quantum teleportation, and you were answering how do people figure this kind of stuff out, and you say it's worth pointing out that quantum mechanics was discovered in 1926 and that quantum teleportation was only discovered in the 90s, and of course quantum computing. I'm a big fan of David Deutsch, and he discovered it, or he thought of it in the 80s. It seems like these ideas were ready to pluck back when quantum mechanics was developed, why did it take so long to have these ideas plugged?
Yeah, that's an extremely interesting question. Um, I mean, the whole idea of thinking about quantum entanglement, and not as something like metaphysically weird or spooky or basically how do we explain this away? How do we get rid of this? But in terms of how do we use it, right? How do we use it for to improve information processing, right? I think that's a point of view that as far as I know, really only started with John Bell in the 1960s, right? With Bell having this remarkable insight that you could do this experiment to test the prediction of entanglement and distinguish it from any possible theory involving local hidden variables, right? And then a little bit later, Stephen Wiesner, had the idea of quantum money, right, or using the uncertainty principle for cryptography. Although he was not able to publish that until the 80s. And there are a few things that I could say here. I mean, one is that when quantum mechanics was discovered in the 20s, it was not at all clear to the people who discovered it that this was sort of a final form that the laws of physics would take, right? They thought, that there was a large contingent that thought that this is some scheme that sort of represents our current knowledge, but clearly one has to improve on it, right? And then that was very much Einstein's point of view, for example, and I think also Schrodinger's, and then like Bohr and Heisenberg, they were very much opposed to looking for something beyond quantum mechanics, but sort of not, they sort of not in a way that was sort of inspiring more research about what you could do with quantum mechanics, right? They just wanted everyone to just sort of shut up and stop asking about these things, right? So you could say, even though Bohr was right and Einstein was wrong on the issue of local hidden variables, there's a deeper sense in which Einstein was the more right one, and sort of putting his finger on there is something here that we do not yet understand and that we need to understand, right? And indeed, that I'm sorry. Indeed, that thing would not be understood really until the discovery of the Bell inequality in the 60s. The other issue is that when quantum mechanics was discovered and into the 30s, there was so much to do in terms of figuring out how chemistry works, right? Just applying quantum mechanics to understanding the real world around us, right? And you could say on the other side, in computer science, for God's sakes, the entire notion of a universal computer was just being born, right? The whole field of classical computing was only just being born, right? So there was sort of so much, on the plates of both sides that it might have seemed wildly premature to anyone to combine the two, right? And then, of course, World War II, intervened with, the people who were doing fundamental science, a lot of them went to work, either at the Manhattan Project or Bletchley Park, and and then after that, I think the theoretical physicists were very focused on just this zoo of new particles that were being discovered, and in formulating quantum field theory. It was very, very much out of fashion for decades to think about the fundamentals of quantum mechanics itself. And in the meantime, people were finally building, commercializing, figuring out the uses for classical computers. That was a very young area itself. And I mean, the entire theory of computational complexity, which is sort of an intellectual prerequisite to quantum computing, right? That only developed in the 1960s, right? And then the theory of P and NP completeness, that was only the 1970s, right? So now, if we think about the people who could have combined these fields, I mean, I think of John von Neumann as an obvious possibility, because he was of course one of the great pioneers of both of computer science and of quantum mechanics. Right. In fact, he invented the notion of entropy of quantum states.
Mm-hmm.
And but he had a lot of other things on his plate, and then he died early. He died in the 50s, right? I mean, Alan Turing was also, of course, a founder of computer science, who was also passionately interested in the foundations of quantum mechanics. As we know from his letters to his friends, he died when he was 42.
Right.
And, so whatever the case, I feel like quantum mechanics and the theory of computing were both in place by the 1930s, but there was a lot of other stuff on people's plates. And the idea of thinking of entanglement as a resource, that only starts in the 60s. Computational complexity, that only starts in the 60s and 70s. And then, maybe a decade after that, people start thinking about quantum computation.
Interesting. I've heard two other theories, and I want to see what you think of them. So the first one is, I think I might be misquoting him, but I think at some point David Deutsch said the reason he was able to think seriously about quantum computing was that he took the many worlds interpretation seriously, and because people before him hadn't taken many worlds seriously, they hadn't been able to go quantum computing. And the second, sorry, go ahead.
Go on. Okay, well, maybe should I respond to that one first?
Yeah.
Okay, so that is definitely true for Deutsch, right? And I know Deutsch well, and he actually became a big believer in the many worlds interpretation when he was here at UT Austin,
right?
As a student, as you know, and he heard Hugh Everett himself give a lecture about it. Bryce DeWitt, who was one of the main early proponents of the many worlds interpretation, was also here at UT Austin, and had a big role, had a big influence on Deutsch. And and Deutsch was thinking about how would you sort of make sort of shake people, how would you sort of make them realize that quantum mechanics is universally valid, that it applies at all scales. Well, if you could build a computer, right, that could do a superposition of different computations, and then you could see the results of interference between them, right? That at that point, conceptually, it is almost like making a superposition over, a brain that can think different thoughts, right? Yeah. And then, if you could have that, then the whole idea of that observers collapse the wave function just by being observers is no longer tenable. But so one problem is that Richard Feynman had the idea of quantum computing around the same time as Deutsch did, right? And Feynman, I mean, he was certainly aware of the many worlds interpretation. He was aware of Everett, but that was not his motivation for thinking about quantum computing. He was, as usual, he was much more practically focused. He was thinking about how do we simulate physics? How do we simulate nature with a computer? And if we use classical computers, we suffer this exponential slowdown, right? And so can we build a new kind of computer that will solve that problem and give us a universal quantum simulator? People were, there was also a whole movement in the 70s and 80s to think about the physics of computation, including like the thermodynamics of computation. Can you make computation inherently reversible? And all kinds of other issues, right? That are not about exponential speed ups. But that was also one of the intellectual streams that sort of led directly to quantum computation, right? So I think that what you said is very much true for Deutsch. but there were others, besides Deutsch who were thinking about these things. Feynman was only one. There were others as well. I think Benioff, and several others. And few people in this field are as uh, uh, um, um, uh, um, as messianic as Deutsch is about the many worlds interpretation.
It's interesting that come to think of it, that both Deutsch and Turing were trying to solve a separate philosophical problem when they came up with their model of computation, or at least in part. Okay, so the second theory I've heard is that since the 1970s, that academia has been less open to new ideas. And you mentioned Wisner, Everett, and both of them, I understand, were kind of I don't know, looked down, ostracized or something. Is that theory confirmed?
I think
to your experience?
it is possible that in some parts of academia, it has become harder to explore new ideas, than it once was. I could believe that about the social sciences. I could believe that, about parts of medicine. People used to do just completely crazy things, just, invent some new concoction, inject themselves with it, see what happens, write an article about it, whereas today, it might take like $1 billion of investment before you could even get to the point where, anyone would consider it remotely ethical to do such a thing, right? So on the other hand, in physics and let's say speculation about the foundations of computing and cosmology and things like that. I think if anything, things have gone in the opposite direction. And then this is partly because we now have this preprint server, this archive, where everyone can post all of their new research ideas with no filter, right? And I think that is somewhat transformed the scientific landscape. Because we still have journals, but journals are now just like a final stamp of approval that in many fields is it's important when you're looking for jobs or things like that, but journals are no longer gatekeepers to that can sort of prevent people from seeing your paper, right? Mm-hmm. And so if you just look at the quantum physics archive every day, you will see so many far out ideas, right? It is so much crazy stuff that it's very hard to believe that a modern day Wiesner or Everett would feel any barrier to getting their idea out there, right? Today the problem is more that like there are so many bold new ideas that of course most of them won't go anywhere, right? Most of them will fail, right? And so there's so much to sift through if you're looking for what is actually going to be revolutionary.
I'm sure your comment section and email fills up with these, but have you how many of the important ideas, or do many important ideas in the field come from people outside academia, or is it mostly people with PhDs working within the system?
Well, okay. Those are not exhaustive categories, right? Because there are there have been breakthroughs that have come from people who are not in academia. Very often, what you find is that these are people who were sort of on the margin of academia, like they got a PhD and then they left the academic world, or they did part of a PhD or things like that, right? There was a famous case of Yitang Zhang, who was this mathematician from China, right, who proved that there are infinitely many pairs of primes, at most 70 million apart, right? Which was a major advance in number theory, right? And this was a guy who had like he had gotten a PhD in math in China, I think, but then moved to the U.S. and then worked making sandwiches at
Oh,
Subway.
wow.
Just in order to like support his family and worked various other odd jobs, but but continued working on math. So I don't, I hear all of the time from, people who are like complete autodidacts, who, taught themselves, yes, and that they think that they've solved the P versus NP problem or whatever, right? That is, that is usually someone who just doesn't understand the question, who has just made some you know, um, and then there is a distinction because sometimes people who sort of teach themselves the field, they just they really want to learn, they just want an expert to talk to, who will tell them like here's where you're on the right track, here's where you made a mistake, and they will thank you for that, right? Other times you get people who really dig in their heels, and the establishment is censoring me, and I had when I taught at MIT, I had someone like writing to the president of MIT to try to get me fired. I had another one sending me death threats, because like very specific. I had to actually contact the police about them, because I would not publish their proof of P equals NP or their refutation of quantum computing on my blog, right? So you get the whole spectrum, but the other thing you find is there are and a lot of the readership of my blog comes from people who studied technical subjects in college, studied CS or math or physics, and then went out into industry, right? But maintain this connection, maintain their sort of curiosity about fundamental questions. And some of those people, actually want to continue to do research. And I'm actually co-authoring a paper with one of them right now. I posted this survey article about the busy beaver function on my blog recently, and there was I guess a hobbyist who solved some of the open problems
Really?
that were in that survey, and yeah, and had a lot of new ideas, and he and I are going to write a paper about it now.
Oh, cool. Interesting.
Yep.
But by the way, is that Chuang the same one that co-authored the Nielsen textbook on quantum information?
No. There's a Yitang Zhang, and then there's it was the mathematician, and then Isaac Chuang
Oh, okay.
is the physicist who co-authored the Nielsen Chuang text.
Okay, got it. My mistake.
Yeah.
So let me ask you about Busy Beaver.
Sure.
Is the proposition 3 was that you can't.
I have no memory for the numbering of propositions. So.
Okay. No, so can you actually just explain what the Busy Beaver function is before I ask you these questions?
Yeah. Okay. Sure. So the busy beaver function is a really remarkable sequence of hyper rapidly growing integers, and the way that we define it, it was invented in 1962 by a mathematician named Tibor Rado, and basically what we do is what we would like to say. Let me start with what we'd like to say. We'd like to say, if I want to name the biggest number that I could possibly think to define, then why not just say, the biggest number that can be named using 1,000 words or fewer, okay, or something like that, right? But then I have to be careful because there's an inherent paradox there, right? Which is I also could have said like 1 plus the biggest number that can be named with 1,000 words or fewer, but then that I just named that with fewer than 1,000 words, right? And so so from this, the conclusion that logicians, philosophers drew more than 100 years ago is that the concept of naming a number, in English is not as clear as we think it is. right? It leads to paradox if you're not careful about it. But what if we could name a number in a way that was completely unambiguous? Well, since Alan Turing in the 1930s, we have had such a way. That way is computer programs, right, or Turing machines. And so we could say, think of the largest integer that can be generated by a computer program that is at most, let's say, 1,000 bits in length. Okay, and now you have to be careful. What do you mean by that? Right, because of course a computer program could run forever. Right, it could start just, we could easily write a program that says do print 9 loop, right, and it would just print an infinite sequence of nines. So what we do is we restrict attention to those computer programs that eventually halt. Right? We say let's say for a given n, we consider all of the possible computer programs that are n bits long, and say there are 2 to the n power of them, or at most 2 to the n power, right? Many strings will just lead to things that are not even programs. They won't even compile, so we'll throw those away, right? Now, among all of the valid n-bit programs, some of them run forever. We just run them on a blank input. So we throw those away as well, right? We consider only the ones that eventually stop. And now, among all of the ones that stop, we take the one that runs for the longest number of steps, the largest number of steps until it stops. And that number of steps, that is what we call the nth busy beaver number.
Yeah.
Right? So the way that Rado defined this was using Turing machines, which is just one particular programming language, the one invented by Alan Turing in the 1930s. He said busy beaver of n is the largest finite number of steps that any n-state Turing machine can run for. Okay, and the amazing thing is that one can prove that this function grows faster than any computable function. Okay, so no matter what sequence of integers, you can basically if you are in a contest to name the largest number, and if you say busy beaver of 1,000, then you will utterly destroy any opponent who doesn't know about the busy beaver function or about anything similar to it. Okay, so one can say further remarkable things about this function, like that only a finite number of values of the function can actually be proven from the axioms of set theory, right? For reasons of Gödel's incompleteness theorem, basically, after a certain finite point, the values of this function, presumably it has definite values, right? Because it's this clearly defined function, and yet we could no longer prove what they are. Okay, so right now only if you take the busy beaver function as Rado defined it in the 60s, only 4 values of the function are known. Okay, the busy beaver of 1 is 1, busy beaver of 2 is 6, busy beaver of 3 is 21, and busy beaver of 4 is 107. Busy beaver of 5, it is only known that it's at least 47 million. Okay, and we don't know how much bigger it might be. Busy beaver of 6, it's at least, I think, about 10 to the 36,000. Okay, might be much bigger. Busy beaver of 7, it's at least 10 to the 10 to the 10 to the 10 to the 18 million. And then it might be enormously larger still. Okay, just to give people an idea of how this function grows.
Yeah. And by the way, I recommend everybody who's listening to check out the Busy Beaver Frontier paper, because it was written in such a way that I also want to ask you how you learned to write so well. It was written in such a way that a non-expert like me could understand it. And just to clarify from my own understanding, it's not that there isn't a function that for any n is greater than busy beaver of n. It's just that it won't. Busy beaver will eventually, with more states than if you have a Turing machine that function, it will grow bigger.
That's exactly what I meant when I said grows faster than.
Right.
I
Yeah.
mean, each particular value of busy beaver is just some positive integer, right?
Yeah.
It's this very concrete thing, right? Like it's 6 or it's 21, right? But if you look at the rate of growth of these integers, right, it will eventually dominate any computable function.
Right.
And in practice, not just eventually, but very, very quickly.
Yeah. And you show very
Yeah.
elegantly in the paper that that means you can independently prove the halting problem and Gödel's incompleteness theorem.
Yeah. I'm looking at. Like the unsolvability of the halting problem, Gödel's theorem. Like these things are so intertwined that like there are many, many different ways to prove them all, right? But the busy beaver function gives you one way that you can prove that that you can use it to prove independently that there is an uncomputable function. You can use it to prove Gödel's incompleteness theorem.
Right. Okay. So the proposition 3 was the one that said
Okay.
that for any axiomatic theory, you can't prove all of busy beaver with it.
Right.
But so my question was, can you keep, even though there's no systematic way to extend our set theory, is there plausibly a way that you can keep extending it such that you can prove higher and higher values of busy beaver?
That's a wonderful question. I would say we don't really know yet, right? Because right now we can't even pin down busy beaver of 5. Okay. Now my guess would be that the resources of existing set theory are perfectly enough to do that, right? But we don't even know that, right? So 4 years ago, a student of mine named Adam Yedidia and I decided to look into a question that for some reason no one had looked at before, which was like what is the smallest n for which we can actually prove that the value of busy beaver of n is independent of set theory, right? Like it was clear that there is some n for which this is true, but are we talking about 10 million or are we talking about 10, right? So in practice, what this problem boils down to is almost like software engineering. Like you have to construct a Turing machine that checks all of the theorems of set theory and that halts only if it finds a contradiction, right? And you have to build such a Turing machine with as few states as possible. Okay, if you can build such a machine with only n states, then you've proven that that set theory cannot determine the value of busy beaver of n. Because if it did, then it would thereby determine its own consistency, which is exactly what Gödel's theorem does not allow, right? So what we managed to do is we managed to find such a machine with 8,000 states. Okay, about 8,000 states. That was after a lot of optimization, right? And a lot of coding and engineering and ideas, right? Since then, a hobbyist, to come back to your earlier question, someone outside academia by the name of Stefan O'Rear has managed to improve our bound and got it to under 800 states.
Yeah.
Okay, and that is the current record. Now, if you could get that down to like, it is a wonderful question. Could you get it down to like 10 states or something like that, right? And that would tell us that we have to already go beyond the current axioms of set theory, even to just get the next few values of the busy beaver function, right? But maybe not. Maybe you can even get 100 of them with existing set theory, right? We don't know. Now, what you can do is, at whatever point, ZF set Zermelo-Fraenkel set theory, which is the accepted basis for most of math. At whatever point it runs out of steam, which we don't know exactly where that point is, but one can then extend it by what are called large cardinal axioms, right? Which basically assert that there exists an infinity that is bigger than any infinity that can be defined in ZF set theory, right? Or you can say where infinities of various particular kinds, right? And and presumably one could then settle more values of the busy beaver function that way, right? But the issue is, no matter what set theory you think of, right? As soon as you can build a Turing machine that enumerates all of the theorems of that set theory, then however many states there are in that Turing machine, that then sets a bound on how many busy beaver numbers
Right.
that set theory can ever determine,
Yeah.
right? So in some sense, the set theories that can determine more and more busy beaver numbers will have to become more and more complicated.
Right.
Right. We know that. And as you said, right, there will never be a systematic way to search for them, because if there were, then that would make the busy beaver function computable.
Right.
And what it means for there to be no systematic way to search is that we could keep like proposing more and more set theories, and if you look at modern mathematical logic, set theorists do this, right? They do propose more and more large cardinal axioms, but sometimes they actually discover that their axioms are inconsistent, right? Or they sort of provisionally adopt an axiom or use it, but the community is not really convinced that it won't lead to an inconsistency, right? So that there's no surefire way to think of these axioms and be confident that you actually still have a consistent system.
Okay, let me offer a very, very silly thought experiment.
Yeah.
Okay, so this is inspired by that joke that if you shoot enough sunlight at the Earth, it'll shoot a Tesla back, right? Okay, so the idea is, if the Turing principle is true, you can simulate the Earth and the solar system and everything on a very incomprehensibly big computer, right? With all the humans on it.
Given the appropriate initial data.
Yeah. And so simulating all of that is a computable function. And if you can check in like every 100 years and see what is the biggest busy beaver number that humans have proven this century, what is the biggest busy beaver number proved 100 centuries, is that not a computable function where that tells you busy beaver of n indefinitely higher, as long as
it would give you a way to compute arbitrary values of the busy beaver function if humans were indeed to continue you could say under the assumptions that number one, everything in our physical world is computable. I mean, we let that, you and I just let that assumption pass almost without comment, right? Although, of course, that's an enormous question in itself, right? With some brilliant people like Penrose on the other side of that. But all right, but and then so assuming that everything we're doing is computable, and also assuming that we could somehow continue finding more and more values of the busy beaver function indefinitely, right? If that were true, then we would have a contradiction.
Yeah. So then either everything is not, either the Turing principle is false, or we can't indefinitely keep extending.
You could say a very conservative way out would be to say, well, our quest to compute more and more busy beaver numbers will come to an end.
Right. Okay, that's very interesting.
And in fact, there has not been another busy beaver number determined since the early 1980s.
Yeah, that's interesting.
Which is when busy beaver 4 was pinned down.
Okay, so I'm looking forward to the paper you published with the hobbyists.
Bruce Smith is his name.
Bruce Smith. Okay, very interesting. Okay, so let me ask you now. I remember in class last year you said, that basically we have a few very important quantum algorithms like Grover's and Shor's that were discovered in the 90s, and now a lot of stuff now is just an extension of those algorithms. What do you think is the potential of finding? Is there a good reason to think that there are other quantum algorithms to be discovered that are as fundamental and important as Grover's and Shor's were?
I would love it if there were, right? I'd be thrilled to discover such an algorithm, have one of my students discover it, right? This is That's the kind of discovery that we enter this field for, right? I mean, if we're being intellectually honest, we have to admit that, it's been 25 years since Grover's algorithm was discovered, right? And maybe no other quantum algorithm as fundamental as Shor's or Grover's has been discovered, in the last 25 years. What we have discovered, as you learned, and because you took my class, was a lot of an enormous number of generalizations and new applications and variations of Shor's and Grover's algorithms, including what are called quantum walk algorithms, including phase estimation based algorithms, um, and some totally different quantum algorithms were also discovered, although the problems they solve are maybe more abstruse, right? Or hard. It's harder to explain what problem they're solving. Uh, and you could wonder, is it lack of imagination on our part, or is it, I mean, another possibility is, if you look at the history of classical computer science, what you find is that there are a few basic techniques that were discovered very early on in the history of classical CS. One of them is dynamic programming,
Mm-hmm.
right? Like, dividing, breaking down your problem like recursively into sub problems, right? I mean, we could say, in general, recursion, right? Solve, divide and conquer, greedy algorithms, convex programming, linear
Right.
programming, uh, you know, uh, um, um, Gaussian elimination, right? And most of the, the field of classical algorithms is enormous, and yet, most of the classical algorithms that we know are somehow built up out of these motifs that were discovered very early on, right?
Mm-hmm.
And we don't normally think of that as a failure of classical algorithms, right? We just think of it as, there are these fundamental features of the algorithmic universe that people noticed as soon as they started looking, right? And then you can go much further, but you go much further by building on the basic things that you have, right? And so maybe we should think of Shor's algorithm and Grover's algorithm not as just specific algorithms, but as sort of some of the basic
Mm,
design motifs of the world of quantum algorithms.
I
And
see.
then, it's not surprising that they were discovered very early on, just like dynamic programming was discovered, right at the beginning of the history of classical algorithms.
Mm,
So, um, so that's one point of view. Now, another point of view is, if like when people ask for more quantum algorithms, or let's say they hold us to account for our failure to discover more quantum algorithms. I like to answer that question with another question, which is, well, what are the problems that you would like these algorithms for, right? And amazingly, that question almost always stops. They ask it, right? Because like they didn't even, because no matter what problem they name, there's an excellent chance that people in quantum algorithms have thought about it. And we know, something about how much speed up you can get from a Grover type algorithm, but we have good reasons to think that you're not going to be able to get better than that, or we say, well, maybe there's, like, if in the case of the graph isomorphism problem, yeah, sure, maybe there's a polynomial time quantum algorithm, but probably just because there's a polynomial time classical algorithm, right? And and it's that hasn't been discovered yet, right? Although there's been major progress toward it. Uh, so no matter what problem they name, right? I mean, probably someone has studied it in the context of quantum algorithms, and I could then tell them for that problem, exactly what is the current situation, and what are people stuck on? And so it might be that if we want to discover fundamentally new quantum algorithms, that the way to do it will be to realize fundamentally new problems, right? Problems that people hadn't even thought about designing an algorithm for, previously, right? The way, another thing, another way that I like to put it is, like in any, in any given area of math or science, right? There is this phenomenon of low-hanging fruit that gets picked very, very early on, right? And then those of us who come into the field a little bit later have to leap higher, if we want to find any fruit, right? But I think the ultimate solution to the problem of low-hanging fruit being picked is to find a new orchard, you know. And so figure out what are potential problems that quantum computers could solve that no one has been thinking about before. Maybe people actually starting to get quantum computers, as they finally are today, that they can experiment with, will help stimulate the discovery of those new problems or new applications.
Just like with Grover's algorithm, is there some reason to expect that from first principles there are other algorithms that can be solved by quantum algorithms?
Yeah, so it is like anything where it's sort of as basic as Grover's algorithm, that you just look at the way that amplitudes are changing over time and think that an algorithm is going to exist, right? That probably would have been snapped up by now, just because quantum algorithms have become so much more sophisticated compared to what they were 25 years ago. Okay, but there are some problems where there's some evidence that a quantum algorithm might exist, even though we don't yet know it, if it does exist. A good example is computing the edit distance between two strings, right? Which means the minimum number of insertions and deletions and changes that I have to make to change one string to another string. This is a fundamental problem for a DNA sequence alignment, for example. The best known algorithm for it takes quadratic time. It's based on dynamic programming, in fact. And there is some evidence that there might be a quantum algorithm that would take n to the 3/2 time or something like that. But if so, it has not yet been discovered. So there are cases like that. No.
Gotcha. Okay. The next question I wanted to ask you was, why do many of the important discoveries, not just in this field, but in many other fields, come from closely communicating groups of collaborators or people within such groups? You said on Sean Carroll's podcast that Shor and Grover were collaborators at Bell Labs. And
well, I'm not sure that they actually were collaborators. I mean, they worked in the same building, I believe. I think I think the discovery of Shor's algorithm created a lot of excitement. All over the place, but certainly at Bell Labs, which is where Shor was, right? And I think that Grover, who worked also at Bell Labs, but in a completely different department, I think he was affected by that excitement. And I'm not even sure if they knew each other prior to Grover's discovery of Grover's algorithm.
Okay.
But I could ask them that. But I mean, more broadly, it is certainly true that in the history of ideas, like major innovations seem to come in clusters all the time. Bell Labs was a huge example of that, right? I mean, the Shor's and Grover's algorithms were really at the tail end, right, of the heyday of Bell Labs, right, which was mostly the 40s, 50s, 60s, 70s, right? But I mean, you had the invention of the transistor, of the communication satellite, and so many other things, right, from this one place. Another example would be I mean, we could take Athens and the ancient world, right? We could take Florence. We could look at Cambridge University, right?
Right.
Let's say, at the turn of the 20th century, right? That had just so many mathematicians, economists, philosophers, physicists who revolutionized the world. Now, this might be because something about the environment, right? That ideas bounce off of each other, right? People see something, they see someone achieve something spectacular, and they're either inspired by that, or they view it as a challenge. They want to compete against that and come up with their own thing, right? A Silicon Valley, of course, would be another big example, although more for technology than for science, right? So that would be one explanation, and a different explanation would be that these certain places at certain points in time just attract all of the people who maybe anyway would have had these great ideas, but that kind of person wants to go to these centers, wherever they are, and so these centers will just collect the kind of people who were likely to discover these things.
Right. Correlation doesn't equal causation in this case. Okay. Let me ask you now. I've interviewed a lot of economists on this podcast. I think this question will be interesting to the listeners. In your paper on why philosophers should care about complexity, you talk about how the difficulty in finding Nash equilibrium might be relevant to discussions on economics. Can you explain this?
Yeah. Okay. So there was a big advance in theoretical computer science 14 years ago, when it was the theoretical evidence was finally discovered for why computing a Nash equilibrium is a hard problem, basically. And this confirmed a suspicion that people had had for a long time, right? Because if we look at a von Neumann equilibrium, right, which is like an equilibrium of let's say of a two-player zero-sum game, right? Then this can be found easily, using linear programming. Okay, but a Nash equilibrium is somehow a more complicated beast, right? And it's the way that Nash proved that they exist in the 50s was using the what's called the Kakutani fixed point theorem, right? It's some fixed point theorem from topology. And if you try to actually unwind the existence proof into an actual algorithm to calculate the equilibrium, then what you get is an algorithm that ends up taking exponential time, right? It eventually hits the equilibrium, but it may have to follow an exponentially long trail before it reaches it. If you're interested in this, by far the best things that have been written about it, I think, are by Christos Papadimitriou. Okay, Papadimitriou was one of the discoverers in in 2006, along with Goldberg and Daskalakis, of this hardness theorem, which it doesn't prove that it's hard to find a Nash equilibrium, and it doesn't even prove that it's NP hard. This problem kind of doesn't have the right structure to be an NP complete problem, just because of Nash's theorem that tells us that a Nash equilibrium always exists, right? Like, in order to be NP complete in any way that we currently understand, there has to be a decision problem. Is there a solution or is there not a solution, right? But for finding a Nash equilibrium, there always is a solution, right? There's only the problem of how to find it. But what was shown is that basically finding a Nash equilibrium is at least as hard as any other problem for which a solution is guaranteed to exist because of the same kinds of principles.
Okay. Yeah.
So it's it is complete for that complexity class of problems for which a solution is guaranteed to exist for this sort of reason. So what does this mean for economics? Yes. Well, it's not clear, right? If it has a sort of direct implication, but it sort of it fits into this general narrative of just because an equilibrium exists, that's not the end of the story, right? I mean, if the market can't actually find the equilibrium, right, in any, or we could say, if calculating this equilibrium would take exponential time, then we shouldn't expect the market to be able to find it either, right? And so, economists are well aware, right, that there are these issues, right, that people are not perfectly rational, even if they want to be perfectly rational, which they don't always. Being perfectly rational might involve computations that they're just not able to do, right? And they've with varying degrees of success, they've tried to account for such phenomena. But I would say, the Nash equilibria are so central to economic theory, right? That the hardness of finding Nash equilibria, I think, is a maybe a non-trivial result, underscoring that general point.
That's incredibly interesting. But do you think Hayek's knowledge problem, or the way he phrased it, might be related to complexity as well? So in terms of like central planning, in order to satisfy some constraints set by bureaucrats, might be like an NP complete problem, where it's like,
well, I want to separate two different things, right? One is lack of knowledge, right, about what is going on in the economy, so forth. And the other one is lack of ability to do computations on the knowledge that you have, right? So the hardness of Nash equilibria is talking about the latter issue.
Yeah,
right?
I see what you're saying.
I mean, they're related in a way, right? They're both, they're both different kinds of deviations from perfect omniscience, right? But they're different kinds of deviations from omniscience. And in theoretical computer science, very, very often we have to distinguish them. I mean, often, like, people will ask me if some problem is or isn't NP complete, when what they really mean is, like, how hard is it to collect the information, right? Which is it's kind of like apples and oranges. It's a category mistake, right? Once it's for like, to even talk about whether a problem is in P or is in NP or whatever, we assume that an input is given to you, right? So all of the information that you need, you have it in front of you. And then, we are exclusively concerned with the difficulty of calculating something about that information, right? Now there is also, the difficulty that, people who are in, economic actors, don't have the information that they need, or certainly central planners, don't have the information that they need, right? And there actually is a whole subfield of economics, that's the economics of information, right? How much do you pay to learn something about, what is going on, or how do you design an auction in a way that you elicit the information that you want from the participants in the auction, and things like that. I think that economists maybe have an easier time dealing with those things, or that stuff has been better integrated into economics than the computational considerations have been.
Okay, that's incredibly interesting. Just a few more questions.
Okay, sure.
Yeah, I'm going to bring us back to David Deutsch and creativity.
Okay.
In the Ask Me Anything chapter of Quantum Computing Since Democritus,
Yes.
you have a student ask you what complexity class is creativity in, and you say, part of what you say is, we've got 1 billion years of natural selection giving us a very good toolbox of heuristics of solving certain kinds of search problems, like problems in NP. But that makes it kind of sound like we have more heuristics to solve these problems than chimpanzees do. Chimpanzees have more than ants. I don't know if this is how you meant it, but do you see like the algorithm for creativity as a thing you have or you don't have? Or is it like you just have better heuristics for searching through different?
I don't know that there is such a thing as the algorithm for creativity, right? In fact, the phrase is almost oxymoronic, right? that if there were such an algorithm, well, then whatever it output would no longer be creative, would it? Because it would just be the output of that algorithm, right?
Yeah.
Uh, so, I think that, um, it seems like there is such a thing as, general purpose reasoning ability, or general purpose ability to invent creative solutions to problems, which, let's say, Einstein had more of than some random person off the street, but the random person off the street has more of than a chimpanzee, and a chimpanzee has more of than an ant. But it is somehow very, very hard to articulate what we mean by that, in a way that would actually support these, comparisons across, vastly different evolutionary histories and goals in life and all these things.
From the beginning to infinity, do you buy David Deutsch's term, a universal explainer, that people are universal explainers, AIs will be universal explainers, but non-human animals aren't, and that's like the only demarcation that matters?
Um, I think Deutsch is like incredibly optimistic and also incredibly categorical in his thinking, right? I don't know anyone else who is sort of as optimistic, or and hardly anyone else who is as black and white, right? I mean, um, it does seem likely that there is some kind of threshold that you cross in going from a chimpanzee to a human, right? Where, like, yes, a chimpanzee is smarter than a cow, right? But, like, if you stare at both of them, it doesn't seem like, the chimpanzee is noticeably closer than the cow is to, being able to land on the moon, right? Or prove Fermat's last theorem, right? Or any of these things, right? And with humans, you had like in succession, you had a few extremely important milestones that that had not been crossed before in the animal kingdom, right? You have universality of language, right? You have, I mean, the ability to have a recursive language that can sort of uh, um, express thoughts of unbounded complexity. You had the invention of writing, the ability to transmit those thoughts across generations. A number system that could refer to arbitrarily large numbers, and then computers, which are universal machines, right? The ability to build these kinds of machines, and all of this went along with being able to explain the world around us in in explicit theories, to an extent that no animal species, no other animal species was ever able to do. Having said that, I don't actually know if people are universal explainers. That is, I have you know, I have no idea if we can explain everything, or even if we can explain everything that is explainable. Of course, I hope that we will continue being able to explain a lot more than we can explain right now, right? But I mean, Deutsch, uses words in unusual ways. Like he, um, like when he talks about why he is so optimistic. Part of his optimism is like, when he uses the word people, he also includes extraterrestrials, right? So he says like, oh yeah, it's possible that humans on Earth will just all kill themselves out. There will be a nuclear war or an environmental catastrophe, but that's not a big deal because people, in the broader sense of life elsewhere in the universe, will go and do all of the amazing things anyway that we would have done. I mean, that may be called comfort to most of us here on Earth, right? And so when he says something like people are universal explainers, you always have to press him on not only what does he mean by a universal explainer, but even what does he mean by people.
Right. His claim on the universal explainer part is that just as many worlds is the most parsimonious way to describe quantum mechanics, so you don't have to like postulate an arbitrary, collapse. Since we have no reason to expect since we have no proof that there are things we cannot explain, the most parsimonious explanation is that we can explain everything.
Okay, I don't know. I mean, there are certain questions like the hard problem of consciousness, let's say, or the question of why is there a universe at all, where it's not just that we don't have an explanation, it's that the mind sort of spins in circles when we try to contemplate what could possibly consist of an explanation, right? What could an explanation possibly look like, even in principle, right? That could just be a lack of imagination, right? But it could be that there are, like we all know, the 2-year-old who just asks why, and then you tell them, and they ask why, and you tell them, and they ask why, and after a half dozen whys, you're all the way back at the Big Bang, right? You're back at the beginning of the universe, and they continue asking why, right? And it could be that there are questions with the property that that every so okay, first of all, I think even Deutsch thinks that we will not, that there is no one time where we'll have an explanation of everything, right? Because Deutsch, says that each question that we answer will lead to further questions, right? Each time you explain something, there's then the question of whatever the explanation is based on, why is that, right? So just like that 2-year-old, right, we can always dig deeper and deeper. Okay, but now just to loop back to earlier in this conversation, like if we think about the busy beaver function, right, we know that it's not just that like with you need more and more resources to compute more and more values of the busy beaver function, and so you'll never know all of them. It's that there are fixed values, like busy beaver of 800, right, where the existing axioms of set theory, provably will not suffice to let you determine that, right? And so likewise, for all I know, there could be fixed questions where maybe the hard problem of consciousness, maybe why is there a universe, where what we currently consider to be an explanation just will not suffice to ever explain these things.
Right.
But I don't know. I feel like unlike Deutsch, I don't want to assert that I know the answer from first principles. I want to continue looking for explanations of these things. It can be, when you're searching for explanations, it can be psychologically helpful to assume that the explanation exists. But let's not make that into more than it is, right? Let's not take a useful heuristic and elevate it into a basic principle of reality.
Right. But on this point, Deutsch wrote a book called The Fabric of Reality, where he talks about how Gödel's incompleteness theorem actually verifies the importance of creativity. So that if we need to come up with new axioms to prove busy beaver of 800, that's the entire point of creativity. And as far as like, I think he thinks the hard problem of consciousness can be solved, but even if it can't be solved, like the reason it's so hard is not because it's not an artifact of our mind. It just seems like we can't imagine a possible mind, and that might itself be an artifact of our mind. We can't imagine a possible way that you could solve it, regardless of what kind of mind you had. The final question is, what advice would you give to a 20-year-old who's interested in technical subjects? Maybe he's not doing a PhD program like you were at the time, but just in college, interested in technical subjects.
just learn all that you can. I mean, there has never been a time when sort of more resources were available to anyone who wants to learn things. Take courses, talk to your professors, um, go on the internet and or read books, delve deeply into a subject, and you might be surprised at sort of how low the barriers sometimes are, right? They're like, if you know let's say that it was quantum computing that you were interested in, right? It doesn't have to be, it could be anything else. But if the entire literature of quantum computing pretty much is available for free on archive.org. And if you go and like look every night at the new quantum computing papers that come out, and just flag the ones that are interesting to you and read them, each paper will raise new questions that the authors don't know the answer to or yet. And sometimes they'll be explicitly listed in an open problem section. Other times, there'll be ones that you could think of, and you can you can study those problems. If you have ideas about them, you can talk to the authors of the paper, and it might take years or decades to become an expert like in a whole field, and you might be very far from that, but it really doesn't take that long to become the world expert on one particular tiny little problem, right? And so try to become the world expert on something, even something very, very narrow, right? And once you've done that, then you can write an article about it, or do a project about it, and then that will lead to more things, right? It will lead to maybe collaborations in the future, and it will lead to you can then try to become an expert on something a little bit wider, and something a little bit wider, and so on.
Yeah, that's very excellent advice. I love that.
Okay.
Well, Professor Aaronson, thank you so much for your time. Hey, if you enjoyed this podcast, please consider sharing it with your friends and posting it on social media. Word of mouth is incredibly valuable for a new and a small podcast like this one. So thanks for watching.